Hello everyone. This is part 3 video on past year NEET questions from the chapter Thermal Properties of Matter and Physics. Now those who are looking at this video can also take a look at the first and second part so that you will have continuity of questions. We will start with a question that is about the thermal radiation. This kind of question has come in multiple years. Assuming the sun to have a spherical outer surface of radius small r radiating like a black body. So we have to assume that the sun is like a black body at a temperature T in Celsius. It is important because in the radiation formula, right, the temperature we use will be temperature on the Kelvin scale. The power received by a unit surface normal to the incident rays at a distance r from the center of the sun is, means what is the situation? You have the sun. Okay, so the radiation power is emerging from the sun. Radiation power that is given by the sun as per the Stephen's law, right? What is it? It will be sigma into sun surface area. Surface area of the sun will be what? Since they are saying it is, we have to assume it like a spherical object of radius smaller. It will be what? 4 pi small r square. Sigma A, this is the formula. Sigma A T power 4 means we have to look at the absolute temperature. Temperature on Kelvin scale means this is the small t is what temperature in Celsius, right? Means we have to add 273. Okay, so 273 power 4. So this is what is the radiation power that is emitted by the sun. Now we have to look at a distance capital R from the center of the sun. So whatever the radiation power given by the sun, right? If you look at how much area it will cover at a distance r, it will basically cover what? A spherical area of 4 pi capital R square, isn't it? So whatever the power emitted, it will go and fall on this 4 pi capital R square area. They are asking us what? The power received per unit surface at a distance r means what? Whatever this power emitted by the sun, this is falling on how much area? 4 pi capital R square, right? So the power received per unit surface at a distance capital R will be what? This much is the radiation power divided by on how much area it is falling, 4 pi capital R square, means what is it? Sigma 4 pi small r square T plus 273 whole power 4 divided by 4 pi capital R square. 4 pi will be cancelled. So what will be the answer? R square is there, numerator, sigma is there, T plus 273 whole power 4. R square is the sigma is there, T plus 273 whole power 4. Denominator, what do we have? Capital R square. So the correct answer for this is what? Option C. So here we are using the Stephen's law and the spread of the radiation. So the sun being a spherical object, the radiation will be spreading in all directions. So if you want to look at on how much area it will be falling at a distance capital R from the sun, the area on which it will fall will be what? Spherical area of 4 pi capital R square. So here they are asking what is the power received per unit surface at a distance r means what? We have to look at what is the total radiation power emitted by the sun divided by the available area at that particular distance. Next we have another question based on the radiation. A black body at 227 degrees Celsius radiates heat at a rate of 7 calories per centimeter square into second. At a temperature of 727 degrees Celsius, the rate of heat radiated in the same units. So here for the black body, if you observe it, right, so they are not giving us the radiation power. What they are giving us, the intensity, means what? The radiation power divided by the surface area. So as per the Stephen's law, what is it? It is nothing but sigma T power 4, assuming it is a black body. Okay, so initially what is the temperature? They are saying 227, right? Means in Kelvin scale, what is it going to be? It will be 500 Kelvin. Now we are changing the temperature to 727. 727 means what? It will be in Kelvin scale 1000 Kelvin. So initially that intensity that is given to us, what is it? 7 calorie per centimeter square into second. That is what? That is equal to sigma into initial temperature is what? 500 power 4. New intensity will be what? Sigma into 1000 power 4. Now the temperature is what? Second case the temperature is 1000 Kelvin. So we have to find this I value, right? What we will do, let us call it as 1 and 2. We will do equation 2 by equation 1. Left hand side what we'll have? I by 7 units we will retain as it is. Right hand side sigma is cancelled. What you have? 1000 power 4 by 500 power 4. So 1000 can be written as what? 2 into 500. So that 500 power 4 will be cancelled. We will just be having what? 2 power 4. 2 power 4 is what? 16. So I will be equal to what? 7 into 16. That will be nothing but 112. Units will be what? Same. Calorie per centimeter square into second. So what is the answer? In the second case, the radiation heat emitted by the black body will be equal to what? 112 calories per centimeter square into second. We'll move on to the next question. This is a question that has come in the year 2009. This is a straightforward question based on the law of conduction. The two ends of a rod length L and a uniform cross section area A are kept at two temperatures T1 and T2. T1 is more than T2. The rate of heat transfer dQ by dt. This is the conduction rate. What do we call it as? We also call it as what? Conduction rate. The conduction rate through the rod in steady state is given by. So once the temperature is established, what is the conduction rate? So look at it. So we have this end temperature T1, that end temperature T2. So the heat will be flowing from high temperature end to the low temperature end. What is the conduction rate formula? Rate of conduction is equal to what? K, which is the thermal conductivity of the material, into A, the area of cross section. Okay, divided by L, the total length, into delta T, temperature difference between the hot and the cold. So what is the correct answer for this? It is option C, Ka by L into T1 minus T2. It's a straightforward question. Okay, the thing is, here if you look at the question statement, they have not mentioned about the K, but we have to assume that K represents what? Thermal conductivity of the rod. Okay, next we have a question based on the temperature conversion. On a new scale of temperature, which is linear, because all the scales, right, the Kelvin scale, Fahrenheit scale, Celsius scale, all of them we call them as what? Linear scales. Okay, the freezing and boiling points of water are 39 and 239. So what is the new scale, right? What is the freezing point? It is 39 degree W. Okay, so this is a different unit. And what is the boiling point of water? 239 degree W. For a normal Celsius scale, what is it? It will be 0 degree Celsius and then 100 degree Celsius. Now the word linear basically means the scale is divided uniformly. That is what it means by linear. Like here Celsius scale will be divided into how many units? Between 0 to 100, 100 equal units. Similarly here, if you see the difference, right, 239 minus 39 means what? It will be 200. This is divided into 200 equal units. What will be the temperature on the new scale corresponding to a temperature of 39 on the Celsius scale? Means they are giving us a Celsius scale temperature of 39. Imagine what is the corresponding temperature on the new scale. See, for this, right, we use the concept of relative distance covered. This is the same principle that we use. Relative distance covered on any linear temperature scale is same. So the same principle we use to convert the temperature from Celsius to Fahrenheit and Celsius to Kelvin, all of them. So what is this relative distance covered means? We have a temperature on Celsius scale. Okay, so the distance covered means what? Celsius value minus initial point is 0. Divided by what is the total length of the scale? 100. This is what is the relative distance covered. In that new scale, let the corresponding temperature is degree W. So degree W minus starting point is 39. Divided by what is the total length of the scale here? 200. So this is what is the relation. Now Celsius, they have given us the value. How much they are saying? Celsius 39. So put the value of 39. So 39 by 100 is equal to what? Degree W minus 39 by 200. We can see one thing, easy cancellation. Okay, so the 2 will go to the left side, it will go to the numerator. So what we will have in the LHS? 79 is equal to degree W minus 39. minus 39 will come to the left hand side, it will become what? Plus. So 78 plus 39, that is our temperature value on the new scale. What is 78 plus 39? It will be, how much it is? It will be 117 in terms of degree W. So what is the correct answer for this? Option D is the right answer. What are we doing? The basic correlation between any linear temperature scale, like the way we do in the case of the Celsius, Fahrenheit and Celsius, Kelvin. So remember there also, what is the idea? We have all the three scales arranged with the reference points. Reference points will be what? The reference points will be melting point of ice and boiling point of water. So melting point of ice, what we can say? We can also say freezing point of water. Okay. So what is the relation? So this problem is over. I'm just trying to recall what we do in the case of the normal temperature conversion. So Kelvin scale means what? 273.15. This is what? 373.15. Then Fahrenheit scale means what? 32 degree Fahrenheit. This is what? 212 degree Fahrenheit. So here it is divided into 100. Here also 100. Here it is what? 180. So any temperature on Celsius scale, corresponding temperature on Kelvin, corresponding temperature in Fahrenheit. What is the relation? Degree Celsius minus 0 by 100 is equal to what? Kelvin minus 273.15. Sometimes you can approximate it as what? 273 divided by 100. That will be equal to what? Fahrenheit minus 32. Starting point. Fahrenheit minus 32 by what is the total scale length here? 180. This is the relation for the three temperature scales. We'll move on to the next question. This is a straightforward question. A black body which is at 727 degrees Celsius emits energy at a rate which is proportional to. So the same model of question we have seen in I think other problems also. See the Stephen's law, right? Stephen's law will give us the expression for the radiation power. Radiation power is what? For a black body, it will be sigma A T to the power of 4. Sigma is the Stephen-Boltzmann constant. A is the surface area from which the emission is happening, and T is the temperature in absolute scale. T is the temperature in the absolute scale. So what do we have? We'll see that the radiation power is proportional to T power 4. So here the temperature given, look at it, it is 727 degrees Celsius. But we should take this into Kelvin, right? Kelvin means what? Add 273. It will become how much? 1000 Kelvin. So what do we see? Radiation power is proportional to what? 1000 power 4. So what is the correct answer for this? It is option A. It's a straightforward question. Next we have a question in 2006. This is based on the Wien's displacement law. A black body which is at 1227 degrees Celsius emits radiations with maximum intensity at a wavelength of 5000 angstroms. If the temperature of the black body is increased by 1000, so we have to be careful about the wordings here. They are saying what? The temperature of the black body is increased by 1000, the maximum intensity will be observed at. So what is the Wien's displacement law? It gives us the wavelength corresponding to the maximum intensity of the energy emitted and the temperature of the black body. What is the relation? Lambda m into T will be a constant, which is what we call as the Wien's constant. What is the value of it? 2.898 into 10 power minus 3. So here the value of the constant is not required for us. This relation. So lambda m into T will be what? Constant. Now if you look at the initial case, what is the temperature of the black body? So here the temperature must be on the Kelvin scale. 1227 means what? Plus 273, that will be 1500. So initially lambda is what? 5000, right? So 5000 angstroms into 1500 Kelvin, that is equal to what? Lambda m dash. When we increase the temperature, see, we are increasing the temperature by what? 1000, means increase of temperature is same on both Kelvin scale and Celsius scale. Why? Because see, if you increase by 1000 means what it becomes? 2227 degrees Celsius. Means in terms of Kelvin it is what? Just do plus 273, that will be what? 2500 Kelvin. We can see also in Kelvin scale, initially what is it? 1500 Kelvin. Plus 1000 means what? 2500, because the unit length the unit length is same on both the scales. That is the reason why whenever we have temperature difference, right? Temperature difference, whatever the temperature difference on Celsius scale, the same value will be there for the temperature difference on the Kelvin scale also. So here the new temperature is what? 2500 Kelvin. Now just we can cancel it of 2500 ones, 2500 twos. Kelvin is also cancelled. What is it? 2 into 1500 means that is 3000 angstroms. That is our lambda m dash. At this new temperature, what is the corresponding wavelength with maximum intensity? It is 3000 angstroms, which is option A. So here we might notice one thing. What is it? If the temperature is increased, the corresponding lambda m value, what is happening? It is decreasing. So initially, what is the temperature? 1500 Kelvin. Lambda m is what? 5000. Finally, what is the temperature? 2500 Kelvin. What is the lambda m? 3000. So as the temperature is increasing means the wavelength corresponding to the maximum intensity radiation will be decreasing. Okay, this point also we can keep a note of it. Next we have another question which is based on the thermal conduction. Which of the following rods, for these rods what they are giving us, the radius and the length are given, each made up of the same material, means what? The thermal conductivity will be same, and whose ends are maintained at the same temperature, means what? The temperature difference between the two ends, delta T, will be same, will conduct most heat, means they are asking in which case the thermal conduction, in which case the thermal conduction is maximum. So remember, thermal conduction depends upon what? If you consider a rod, thermal conduction depends upon what? It depends upon the thermal conductivity value K, area of cross section. So here we are assuming to be like what? Cylindrical rod. That's why they are giving us the radius. So area will be what? Pi r square. It depends upon the length and of course the temperature difference between the ends. So look at it, the rate of conduction. Rate of conduction, what is the formula? It is Ka into T1 minus T2. So T1 and T2, let us consider them as what? The temperatures at both the ends of the rod. So one end it is T1, other end it is T2. Here we take that T1 is more than T2. Okay. So Ka into T1 minus T2 by L, that is the rate of conduction. Okay. Into time. So we multiply this by time means what? It will give us the total amount of heat that is conducted. So rate of conduction is what? This one. Ka into T1 minus T2 by L. Multiply by time means what? You will get the total conduction. So here anyway, the thing is what? Between these rods, where is the difference coming? So by the way, A is what? Pi r square. The difference is coming where? The difference is coming in the value of R and the L. The rest all quantities are same. Okay. So we have to look at each of these options and then conclude which of them is going to give us the maximum heat through the conduction. Okay. So look at it now. We'll have to go one by one. There is no other option. Option A. R is equal to R naught, L is equal to L naught, means what? K into pi R naught square T1 minus T2 into small t by L naught. Option B is what? R is 2R naught, L is L naught. So K into, here we will get 2R naught the square, means it will become what? 4R naught square. So K into, maybe we will bring the 4 to the front, 4K pi R naught square T1 minus T2 into small t by L naught. That is our option B. So we have to look at each of these options, what will be the value of the expression. That's it. Other than that, there is nothing else. It's also a straightforward question. The only thing is we have to take a look at each of these options and then we will be able to conclude. Now come to the option C. R is R naught, L is 2L naught, means what? Option C, K into pi R naught square T1 minus T2 into small t by 2 times L naught. There is a 2 in the denominator. Okay. Now option D is what? R is a 2R naught, L is 2L naught. So numerator will get a 4 because the 2R naught square means it will become 4. Denominator will have a 2. So look at it. 4 by 2 k pi r naught square into t1 minus t2 into small t by L naught. Numerator will have a 4, denominator 2. Means what totally it will be 2. Now just look at it. The entire term, this is as it is. K into pi r naught square into t1 minus t2 into small t by L naught is same. In option B it is multiplied by 4. Option A it is multiplied by 1. Option C it is multiplied by a factor what? Half. 1 by 2. Option D it is multiplied by a factor 2. In which case it is maximum? In case of option B. That is where our heat through conduction is actually maximum. Okay, so here once we write down that expression, right, the heat through conduction, that is what? Rate of conduction multiplied by the time. So here in all the cases time is assumed same. That is why that is not coming into picture. Okay, so what is the answer for this? It is option B. Next we have another straightforward question based on the Wien's displacement law. This has come in the year 2004. If lambda m denotes the wavelength at which the radiation or radiative emission from a black body at a given temperature is maximum, means this is what is the wavelength corresponding to maximum intensity of the radiation that is emitted by the black body. The black body is emitted at temperature T. Then they are asking the relation. What is the relation? Lambda m into T is equal to Wien's constant B, right? So if you see, what is it? Lambda m will be equal to B by T or B into T power minus 1. So what is the relation we see? Lambda is proportional to what? T power minus 1. So what is the correct answer for this? Option D. It's a straight question. Next we have a very important model question. This has come in the year 2003. So this is based on the idea of the equivalent thermal conductivity. Even in one of the previous videos also we have seen how do we calculate the equivalent thermal conductivity. So we have seen I think in part 1 video or part 2 video we had a question like that. Maybe you can go back and refer to that also. So here we will see what is the question all about. Consider a compound slab consisting of two different materials having equal thickness. Means the compound slab is made by using what? Two separate slabs. Both are having equal thickness. The thermal conductivities are K and 2K. Thermal conductivities of the material are what? K and 2K. The equivalent thermal conductivity of the slab is how much? So they are asking what is the equivalent thermal conductivity of the slab. So if you look at it, right, we are making a compound slab, means there are actually two ways of doing it. One is like say this is the material whose conductivity is K, area of cross section is A, and length, let us say L. Here they didn't even talk about the length part. So we can keep them like this in parallel. So this kind of arrangement we call it as what? Parallel arrangement. Or we can have one more arrangement like this. This is what we call as series arrangement. Okay, so this we call as what? The parallel arrangement, and this we call as the series arrangement. Now before we go on proceeding with the particular question, the way we will approach finding of this equivalent thermal conductivity, right, will be similar to the way we will solve the problems involving equivalent resistance in electric current chapter. So normally if you have a resistance, what is the, say for example, resistance of value R, and we apply a potential difference delta V. What is the electric current through that resistance? Delta V by R. So here the current is driven by what? The potential difference. Similarly, if you look at thermal current, the heat flow through conduction can be also called as what? Thermal current. The amount of heat flowing in given time. That is what? Thermal current, which is nothing but the amount of heat going through that particular object through conduction divided by the time taken. Thermal current will be what? Ka by L into delta T. So here delta T is the temperature difference between the two ends. That is the driving force here. Now if you are to arrange this just like the electric current expression, right, what we can say? Delta T divided by L by Ka will come. So this is like what? The driving force divided by some term. This term is what? This is the equivalent This is the equivalent of resistance. That is the reason why we also call it as what? Thermal resistance. We also call it as what? Thermal resistance. Now the approach is like this. If you have resistors in series, this is something that we learn in the 10th standard itself. Resistors in series means what? R equivalent is equal to R1 plus R2. Resistors in parallel means what? 1 by R1 is plus 1 by R2 is equal to 1 by R equivalent, isn't it? The resistance series means what? If you have a combination of resistance in series, what is it? R1 plus R2 is equal to R equivalent. Parallel means what? How many ever we have? 1 by R1 plus 1 by R2. If you have one more means 1 by R3 will come like that. Is equal to 1 by R equivalent. So these are the relations for the series and parallel equivalent resistance formula. Now in the case of the thermal resistance also, we'll use the same approach. So if you have slabs in series means what? Thermal resistance also, equivalent thermal resistance is what? R1 plus R2. Series means, parallel means what? 1 by R1 plus 1 by R2 is equal to 1 by R equivalent. Now let us come to the problem that we have. So they are saying there are two slabs. Here this question is also a little bit ambiguous. Why means? They did not say exactly how the compound slab is obtained. Means this will leave the ambiguity, whether it is a parallel arrangement or it is a series. So first let us look at the series arrangement. So first slab, length is L, conductivity K, area of cross section A. So what is the R1 here? L by Ka. Okay, so what is the second one? R2 will be what? Length is same, area of cross section is same, but conductivity is 2K, means it is what? L by 2K into A, that is R2. Series means what is the relation? 1 by series means R1 plus R2 is equal to R equivalent, right? So R1 is what? L by Ka plus R2 is what? L by 2Ka, that is equal to R equivalent. R equivalent means what? We have to replace this entire thing by a single material. Imagine, with a thermal conductivity K equivalent. This is what they are asking, equivalent thermal conductivity. What is the area of cross section of the slab? A, but length will be 2L. Why? Because it has to replace the entire combination, right? Means length will be what? 2L. Now look at it. R equivalent will be what? Length in this case is 2L divided by K equivalent into A. So here we can see that left hand side is what? Take an LCM means it will be what? 3L by 2Ka is equal to 2L by K equivalent into A. So L is cancelled, A is also cancelled. So what do we have? Cross multiplying means K equivalent will be what? 4K by 3. This is what we'll get when we take a series arrangement. Okay, that's the answer that we can conclude. As I said, right, this question is ambiguous because they have not clearly mentioned. So ideally what would be happening is they would be clearly mentioning whether it is a series arrangement or the parallel arrangement. In fact, in the previous question that we solved in one of the recent years, right, they have even depicted how the arrangement is. Whether the arrangement is series or parallel, they would even depict in a diagram and show it to us so that there will be no ambiguity at all. But if you were to do this problem by using parallel combinations, we'll have a doubt, right? You know, if somebody will take the parallel combination, since they have not clearly mentioned what is going to happen. So look at it. If instead of taking a series, we take it like a parallel, imagine. So this is the slab 1, conductivity K, area of cross section A, length L. Second slab, this is the parallel arrangement. Conductivity is 2K, area is A, and length is L. We replace both of them by equivalent slab, means its length will be L, but area of cross section will be 2A. Look at it. A plus A will be what? 2A. And the equivalent thermal conductivity K equivalent. Now what is the relation? Parallel means what? 1 by R1 plus 1 by R2 is equal to 1 by R equivalent. So let us just write down. R1 is what? L by Ka. R2 is what? L by 2K into A. R equivalent is what? L by K equivalent into 2A, that is R equivalent. Now what is the relation? 1 by R1 plus 1 by R2 is equal to 1 by R equivalent, right? This is the parallel arrangement. So 1 by R1 means what? Ka by L plus 1 by R2 means what? 2 Ka by L is equal to 1 by R equivalent means what? K equivalent into 2A by L. So we'll see both sides, the L in the denominator cancel. Left hand side is what? 3 Ka is equal to K equivalent into 2A. A also cancelled. Bring the 2 to the left side. What we'll have? 3 by 2 into K. That is our K equivalent. We'll see that option is not there. So which means, we can conclude that, okay, so this is probably the series arrangement that they're talking about. So such ambiguous questions, right? They would be definitely challenged, but if you want to get the answer means you can look at the both possibilities. If at all you feel that there is an ambiguity. Otherwise, if they clearly depict the diagram, like I think in one of the previous question, right, they have depicted this diagram, like arrangement of the slabs like this. So through one slab, heat will flow like that. To other slab also heat will flow. That is why we said parallel. Heat is going to flow parallelly through both the slabs. That's why it is called as parallel. The previous arrangement is what? First the heat will go through the first slab, then it has to go through the second slab. That is what we call as the series arrangement. Okay. So this is how we are going to approach the problems which have the equivalent thermal conductivity. Just like the way we solve equivalent resistance in case of the normal electrical resistances, right? Same approach. So the one thing that we need to keep in mind is the thermal resistance is what? L, length of the slab divided by K, thermal conductivity into area of cross section. That part we remember. So once we remember that thermal resistance value, right, we can just do the problems like the way we do in simple combination of resistances in series and parallel, like the way we will have in current electricity. Okay. So this is about the question on the equivalent thermal conductivity of the slab. So make sure that you go through the other problem also that we discussed in the part 1 or part 2, so that you have a complete understanding of this. This is an important model. So with this we complete the part 3 discussion, and we will see in the next part video.